Hello, in this video we're going to look at sequences of functions, and then specifically we're going to look at pointwise and uniform convergence of this sequence of functions. So first let's let D be a subset of the real numbers, and then for each n we're going to let f of n be a function for x, of course, in this subset D of the real numbers. And then if we write it like this, that the function f of n goes from D to the real numbers, then we say this sequence f of n is a sequence of real numbers. Okay. So here I put properties in question mark, and so so if x is an element in D and f of n is convergent, remember this is just a sequence of real numbers. So pick an x, then f of n as n goes to infinity, that this is just a sequence of numbers. So we can ask the question, does it diverge or does it converge? So let's assume that it's convergent. And then we set f of x to this limit like this. F of x is equal to the limit of f of n of x. Now what properties does f inherit from f of n? Right? And the quick answer is not much. Now the following properties do not carry over from f of n to f. You know, one-to-one, increasing, decreasing, bounded, continuous, differentiable, integrable. So not much carries over. So what we're going to try to do in the upcoming videos is introduce some criteria that if f of n's meet, then that carries over to f. Okay. And two of those properties is pointwise convergence and uniform convergence, which we'll talk about on the second page. But first I want to point out a theorem here that we sort of talked about in the first video on this playlist. Let's assume this series converges. Remember, these are real numbers. F of n converges to f and g of n converges to g on both on the set D, which is a subset of the real numbers, and this is for each x. So for a given x, these converge. Then the following hold. The c times f of n converges to cf. Fn plus gn converges to f plus g. The products converge. The ratio converges, you know, assuming that the denominator is not zero. And we get all these because these are just sequences of real numbers. And so if you go back and look at the proof of adding, multiplying, and dividing convergent sequences of real numbers, that's the proof to prove these. So we're not going to do it here. So let's look at the pointwise limit. So let's let x be in a subset or a set D, which is a subset of the real numbers. Then for each n, f of n is a function on D. So let's assume that f of n, this sequence f of n, is convergent for each x, you know, in this subset D, in this set D. And let's define f to be this limit. Then given epsilon greater than 0 and x, such that n, there exists an n such that little n greater than big N, we have that the difference between f of n and f is less than epsilon. They're really small, meaning that f of n is converging to f. Okay, f is called the pointwise limit of the sequence f of n, and here's a note that n depends upon both epsilon and x. So here it's given epsilon and given a point x, then there exists an n. So this is really a function of x and epsilon. Okay, that's pointwise limit. Now the uniform limit, let's let f of n converge pointwise to f on this set D. The function f is called the uniform limit of the sequence f of n if given epsilon greater than 0, there exists an n such that little n greater than n, we have that f of n minus f is less than epsilon. And this is for all x. Okay, so here's a couple notes, and that this n right here does not depend upon x, only epsilon. So given epsilon, then there exists an n such that they're really close. And this is for every x that we want to pick in the interval D. It doesn't matter. They're all really close on every x. Okay. We say f of n converges uniformly to f on D. And this is the language we're going to use in upcoming videos. And here's a note that the supremum of this difference over all x in our set less than the epsilon is the same as that this difference is less than epsilon for all x, right? So if the largest difference for all x is less than epsilon, then surely the difference is less than epsilon for all x. And really this is an if and only if, and they can be interchanged. Some write it like this and some write it like this, and we'll probably stick with this notation. Now when uniform convergence is met, so f of n converges uniformly to f, then many properties from f of n carry over to f, and that's what the next few videos are going to pertain to, is what properties do carry over, and we'll take a look at that. Well, that's all I have for today. Hopefully you enjoyed that. If you did, please like the video and subscribe so you don't miss the next one. Thanks. Bye.